Hello everyone. Let us now discuss the raised cosine pulses and the condition for zero ISI, which is actually the Nyquist condition for ISI free communication. Now we have been very familiar with this block diagram in which the P1T is the pulse which will actually represent the digital bit stream. It passes through the channel. The channel impulse response is, let's say, CT. Then this P1T gets convolved with CT, and again a PAM pulse, but of course distorted and noisy pulse will be generated, and we call that pulse as P2T. And I'm showing here the noise is also added. Now at the receiver end, the P2T pulse will be received, and P2T will get convolved with the impulse response of this receiver filter to generate another pulse, P3T, which is again a PAM pulse, but after it has gone through the channel and the receiver filter. And then we will do the sampling here after every capital T seconds to receive the to make the decision and to detect the input what was transmitted. The point that I'm trying to convey here is that there are three pulses I'm talking about. One is P1T, which is the initial pulse, P2T after the channel, and P3T after it is received by the matched filter or the receiver filter. Right. So channel is random. It is not in the control of the designer. The receiver filter, we are saying that the optimum receiver filter or the matched filter should be the impulse response of this filter should be matched to the P2T pulse. Right. So P2T is the result of the P1T passing through the channel. So that means all in all, we have only this P1T. The designer has got control over this P1T pulse only, that how to design the shape of this pulse so that the optimum receiver can be designed. And once the bit stream is traveling through the channel, the waveform should not spill over from one symbol period to the other symbol period. I mean, there should not be any intersymbol interference. So that's the goal to achieve in this lecture. Meaning by that, what I want to say is that we have the control over only this P1T pulse. So that means we have to design this pulse in such a way so that we can receive an ISI free communication. So let us see how the things can be developed further. Now to design P1T, ISI should be made to 0, that is, it should be eliminated. We know that what is xt? Xt, as I have described here, xt is the transmitted signal consisting of sigma k going from minus infinity ak P1T minus k capital T, actual transmitted signal waveform representing the digital bit stream. Right. So what is yt? Yt is the result of the convolution of xt with the channel response and plus noise added, of course. And then yt is the signal which is received here in the form of P3T pulses. Right. It comes after the P1T or xt. P1T is the waveform, xt is this transmitted, complete transmitted signal. It gets convolved with CT, then noise is added, then the whole noisy signal gets convolved with this impulse response. So that's what is shown here. K is replaced. Now one modification I'm doing here is that I'm replacing this K with an index M. So the resultant YT waveform will be sigma M going from minus infinity to infinity AM. So that means in place of K I'm putting M. P1T of M, P1T minus M capital T, convolution with CT and convolution with AT, and this AT will also get convolved with the noise, right? And P1T, when it gets convolved with CT and AT, it results into P3 T minus MT. So that's the resultant received waveform that we will receive. And after receiving this waveform, that means this is my received signal, and this received signal has to be sampled at every t seconds, capital T second. Every symbol period it has to be sampled. Because when we will sample at every capital T seconds, then the signal to noise ratio we will achieve, that will be the maximum. Now we will sample yt after every capital T seconds, so that kth sample. Now this yt, this is a variable, small t is there. Now we want to sample it at a particular instant, capital T, and I replace this and I place this k index representing the time instants. So k will vary, the values of the k will determine what are the time instants at which we are sampling, right? So that's why we actually got this k index free from here, and in place of k I put m. So ykt, this is the sampled version of yt at a particular instant, capital T, after every particular after every capital T seconds, because we have to sample. So that means this small t has to be replaced with k capital T. So am p3 k capital T minus m capital T plus, of course, this convolution of noise with impulse response of the match filter, and this has also to be sampled at t equal to k capital T, right? Now if you look closely this expression, you will see that it is a convolution of the two sequences, two discrete sequences. So let us discuss about that. So AM is a discrete time signal. So AM here is a discrete time signal, of course, and BM, let's say, which is P3M capital T. I am representing this part of the expression with the BM, B subscript M. This is also a discrete signal. This is also a discrete time sequence, P3MT. So that means there, what is happening? There is a convolution taking place between the two discrete sequences. So convolution of two discrete time sequences at k is given by. So this is the resultant sequence after the convolution has been performed between AM and BM. So we can this is CK. So CK can be represented as the discrete time convolution, in the discrete convolution in the discrete domain, and this is equal to, of course, AM P3 K capital T minus M capital T. So we can represent the convolution of the two sequences in this form. Now convolution of two sequences evaluated at kth sample. So we are evaluating the convolution. So if you look at the, so this is the convolution in the time domain, right? This is for the received signal. Now when we are sampling this convolution, we are saying that we are sampling at every capital T seconds, and we are putting an index k here representing the time instants at which we are sampling. So ykt equal to sigma m going from minus infinity to infinity, am p3 k capital T minus m capital T, and plus this convolution, noise convolution part. As I said, this AM is a discrete sequence. P3 MT I am representing with BM is another discrete sequence. The convolution of the two discrete sequence will be a third discrete sequence, and which is evaluated at kth sample. All right. So ykt at the kth sample, that means the kth sample has arrived, and we are doing the sampling. So it will be equal to ak convolution. So since this is representing the convolution, we can put it like this: ak convolution p3 k capital T plus this noise part, because noise also the convolution of the noise with the impulse response of the match filter also gets sampled at t equal to k capital T, right? So this is the noise sample that will be after the sampling. Now when we put m equal to k, we get, when we put m equal to k, so this will be p3 of 0. So we can say that ykt equal to ak, p3 is 0. What it is representing? It is representing, so k means the kth sample, right? So m means the timing instant. So when the kth sample, right, is actually our present sample. So that's why I say k equal to m. The kth symbol value, right, which gives the information about the actually when k equal to m, that means this kth symbol value gives information about ak. So this is the present symbol that we are interested in when m equal to k. And now what we are doing, actually we are putting k equal to m, so that means we get ak p30, right, for when m is equal to k. So we can extract this term out from this expression, all right, plus um, what is there in this part, y of kt will be equal to uh, m going from minus infinity to infinity, right, when m is not equal to k. So when m is not equal to k, right, because we have extracted this term out, we have extracted when m is equal to k this out, I have separated out this term which is representing for the information present in the present symbol that we are interested in, and this is the rest of the equation plus noise, of course. Now this is what this term which I have shown in a dotted with a dotted line is the information of the previous symbols, right, which is interacting with the present symbol, and we are detecting this sample what was actually transmitted. We are trying to estimate what bits or what ak was transmitted, but we have the ak information, of course, but it is also uh, it is also suffering from the information spilling over into this present symbol from the previous symbols, right. This is known as the intersymbol interference. So this part of the expression when m is not equal to k actually represents intersymbol interference. Okay, now we know that this is the ISI part, right. Now if we have to make the communication system ISI free, that means intersymbol interference free, we have to make this term which is shown in the dotted lines must be equal to 0. Then only the received sample, which is actually the sampled version of yt, will give me the information about only the present symbol. No ISI will be present. Let us look at this concept. And for the sake of simplicity, I'm just getting rid of this P3T, because earlier I used P1T, P2T. I'm replacing this pulse with GT now. And we want, of course, ISI to be equal to 0. I'm writing the expression, the previous expression in the previous, that means in the previous slide, this expression, this whole expression I'm writing again in terms of P3. Then after this, I will change um, P3T with GT. I want this ISI term should be 0 to make the communication system ISI free. This is the noise part, of course. Now, if you look carefully, what is happening? What is YKT? YKT is actually the convolution of AK and P3KT, right? And the result is sampled at a particular time instant. So, if you look at the point that I'm trying to make is that this is the result of the convolution of AK with P3KT. Now I want to make this term as 0. When this will happen? This will happen only when the convolution of AK P3KT generates only one non-zero sample and all other samples must go to 0. This whole expression is actually the convolution of AK P3KT. I want ISI to be 0. This can only happen when it generates only one non-zero sample, so that there are no other samples which can spill over with the present in the present symbol time period. So all other samples must go to 0, and this convolution, and this can happen because this is the convolution taking place. We want only one non-zero sample. This can only happen. Now I am replacing this P3KT with GKT. This will happen only when, if it happens, it will be equal to AK G0. That means this is the present sample. And this is true if and only if GKT, this GKT is a delta sequence. When this is a delta sequence, then only there will be only one non-zero sample, and all other samples will be zero. So I can say that GKT equal to delta K. Now GKT equal to delta K, that I am taking from here on onwards. GKT is what? GKT is the sampled version of GT. GT is the pulse received after the matched filter. So GKT is actually the sampled version of GT. Now if I replace this, if I take the time domain version of the GT, right? So that means if I write for GT instead of the sampled version of sampled version of GT, I can write it to be like this. Because it is GKT, this is the sampled version. I can write it GTK going from minus infinity to infinity delta T minus KT, which is equal to delta T. So I am writing the not the sampled version, but the time domain version of the this sampled version. All right. Now let us take the Fourier transform of this formula of GT delta T minus KT equal to delta T. Let's take the Fourier transform here. This is the multiplication of the two sequences, two signals, sorry, GT with this one. And when there is a multiplication in the time domain, in the frequency domain, it will be the convolution. So that means GT will give me GF, convolution with delta F minus M by capital T. I'm just replacing the indices. Okay, with K with the M. In the frequency domain, I'm using M. Right, F minus M by T equal to 1. This is the Fourier transform of this expression. This is delta T, it will be equal to 1, the Fourier transform. Now what is this? And we can take now the sigma out from this convolution, and when when GF gets convolved with delta F minus MT, so what we will get is G of F minus M by T. So this is the expression. This is most important expression for getting ISI free communication, which says that sigma M going from minus infinity to infinity, G of F minus M by T equal to 1. This is the Nyquist expression for zero ISI. That is, this expression has resulted when we want to make ISI to be 0. When we are saying that we are making this term as 0, and we are checking the conditions when this term will go to 0. This term will go to 0 when it will be a delta sequence. And we are writing just the time domain expression, and we are doing the Fourier transform, and we get this. Let's plot this expression. If you plot this expression, what is this expression saying? G is the spectrum of the G in terms of the G in the Fourier GT in the when you take the Fourier transform. That means we are representing the spectrum of the GT pulse. Now what this expression says? It says the spectrum well, this is the sigma. It is going from minus infinity to infinity. That means this is representing a spectrum which is repeating after every 1 by T frequency, right? So let us see that after every 1 by T, this expression, the spectra is repeating. This is the spectrum, this is the spectrum, this is the spectrum. And what it says that the summation of all the spectrum spaced after every 1 by T, the summation of all the spectra spaced after every 1 by T frequency should be equal to a constant. Should result, the addition of these spectra should result to 1. Now what I mean to say is that if you look along the x-axis, at every point all the spectra should sum to 1 or constant. That is the Nyquist condition for 0 ISI. So we know that sampled at gt equal to p3t, that is um, spectrum of gt should look like as shown in the figure, and when the spectrum which is spaced at multiples of 1 by t should sum to 1 or constant value. This is the condition for 0 ISI and is also known as Nyquist condition for 0 ISI. Nyquist, so I am again writing Nyquist condition for 0 ISI is sigma m going from minus infinity to infinity g of f minus m by t equal to 1. So let us discuss different cases to design P3T or GT, because this is what? This is the representation of the spectra of the pulse that we received after the matched filter. So what was the starting point? The starting point was P1T. P1T was a shape of the pulse that we used to represent digital data, ones or zeros. What shape we should choose of that pulse so that this expression is true? That is the only thing which is in the hands of the designer to make an ISI free communication system. Let us look at some cases for GT, which in turn actually we are looking for P1T. What should be P1T? So that when it results into GT, the sum should result into the summation of all the spectra should result into a constant value. So GF is equal to 0 for for a band limited version of GF. Within the bandwidth, outside the bandwidth, it has to be 0, and within the bandwidth it has to be some expression. Now when the bandwidth is less than 1 by 2t, what will happen? When the bandwidth is less than 1 by 2t, so the expression goes like this, right? That means uh, the spectra of the pulse is not overlapping, and at certain points you will see that it is not going to a constant value or 1. Impossible to have 0 ISI for this case. Let's look at the second case when b is equal to when this bandwidth is equal to 1 over 2t. In that case, this is the bandwidth, this is the band limited version of the spectra, right, of GF. Now at so you it is clear that at all the points it is not 1, it is not leading to 1. The summation of the spectra is not leading to 1 when b equal to 1. This can lead to 1 only when we choose a pulse shape to be rectangular. ISI is not 0 in this case also, except if we choose rectangular pulse, but it will be very strict restriction, which is practically not possible because we cannot generate absolutely rectangular pulses, because there has to be certain roll off. So in that case, the ISI condition will not, 0 ISI condition will not be true. Now what is the third case? When B is greater than T. What is B? B is the bandwidth of the pulse that we are choosing. We are band limiting the pulse, and B is the band, and when it is greater than 1 by 2T, that means the spectra are overlapping with each other. Now if you can see and do the summation of the spectra, you can achieve a constant result after summation of all the spectra. Even if the spectra samples, even if the spectra overlaps, but it will satisfy the Nyquist 0 ISI condition. So pulses that we should choose must be overlapping with each other, right? So we know that P3T equal to GT, right? I am representing the diagram once again. This is my P1T, this is my channel filter. After the channel filter is P2T, then receiver filter is there, and we get P3T. I'm just avoiding noise here. So how should I achieve the 0 ISI condition? Now raised cosine pulses represent a class of pulses which can satisfy Nyquist 0 ISI condition. So what are raised cosine pulses? Raised cosine pulses can be represented as gt equal to sine of pi t divided by capital T, pi t divided by capital. So this is the sinc function basically. So this gt is equal to sinc of pi small t divided by capital T into cos pi alpha square alpha t divided by t, and in the denominator it is 1 minus 4 alpha square t capital T square. This is the extra term because these are the raised cosine pulses. This is the sinc function, and this is the extra term present in the raised cosine pulses. Now if you, this is my raised cosine pulses in the time domain. Now if I try to, I'm not doing the Fourier transform, but I'm straightway putting the Fourier transform of the raised cosine pulses. So GF will be equal to capital T. Within this 1 minus alpha by 2t, it is t cos square pi capital T 2 alpha in this range, right? And beyond this range it will be equal to 0. So if I represent it like this, now the slope of this pulse will depend on alpha. This point is minus 1 over 2t, this point is 1 over 2t, right? So when alpha is equal to 0, when alpha you put it equal to 0, the frequency range will be from minus 1 by 2t to 1 by 2t, right? Now if you put alpha for any other value of alpha other than 0, the 1 minus alpha by 2t will lie within this range. It will be smaller than either minus 1 by 2t or 1 by 2t plus 1 by 2t when alpha will have certain value. When alpha equal to 0, so this will be a rectangular pulse. Now the slope depends on alpha. It's the slope of because within this 1 minus 1 plus, I mean 1 minus alpha 2t, this expression, this is minus 1 by 2t, this is 1 by 2t. Beyond this is 1 plus alpha by 2t. So it will extend beyond 1 by 2t on the positive side and minus 1 by 2t on the negative side, right? And it will extend up to 1 plus alpha by 2t. So this waveform will extend beyond 1 by 2t on the positive side and beyond minus 1 by 2t on the negative side, and will go up to 1 plus alpha by 2t. Beyond 1 plus alpha by 2t on the positive and the negative side, it will be 0. That's what this expression is saying. And the slope of this waveform will actually depend on the value of alpha, because alpha is of course positive here. So when alpha equal to 0, so it will be a rectangular pulse. So the afterwards, so it will be rectangular in the time domain or rectangular in the frequency domain. If you take the inverse Fourier transform, it will in the time domain it will be a sinc function. So this sinc function represents the alpha equal to 0. For alpha equal to 0.5 or even alpha equal to 1, the time domain version of these raised cosine pulses will be sinc function only, and after some values of alpha this will cross no, this is for this is alpha equal to 1, this is alpha equal to 1, which the waveform has crossed this 0 axis, x-axis, and this is for alpha equal to 0.5. It is not crossing, but it is going like this. So when it becomes alpha equal to 1, so it will cross like this and it will get it like. So these are different values of alpha. What I want to say is that the for different value, for alpha equal to 0 in the frequency domain it will be a rectangular pulse. For alpha other values other than 0 it will be a waveform. And if you try to take the inverse Fourier transform, that means you want to come to the time domain waveform, it will be a sinc function. So for alpha equal to 0, gt will be a sinc function. In frequency domain it was a rectangle, right? So I finish my lecture here. So I will continue with the digital communication, and we will discuss about the modulation techniques in the next lecture. Thank you so much. Thank you.